Hello everyone, I am Akhilesh Kumar Shrivastava from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we have discussed about the deadlocks, how can the deadlocks be represented in the computer system, and we have discussed about the methods for handling the deadlocks. In today's lecture, we will see another schemes by which the deadlock can be handled, known as the deadlock detection and recovery scheme. So, the outline of today's lecture will be that we will first have a look at what are the techniques and what are the basics for the deadlocks, and what are the techniques that we have discussed for handling the deadlock in the previous turns, for example, deadlock avoidance and deadlock prevention. Finally, we will go for the deadlock detection and the recovery schemes. Now, this was the diagram that we took in on the last turn as well. This is showing the diagram of a four-way crossing, wherein the vehicles are coming from this side and they wish to go here, and vehicles are coming from this side and they wish to go there. Vehicles coming from this side want to go there, and vehicles coming from this side want to go there. So, actually the movement of any of these vehicles is not possible. Movements of any of these vehicles will not be possible, and because of that we can say that there is a deadlock here, or we can say that there is a condition of the bottleneck here. Now, in the next diagram, this is representing the connecting four-way crossings. So, the vehicles are coming from this side and they wish to go there, but does not look like they will move. The vehicles are coming from this side and want to go there, does not look like it will be possible. Vehicles coming from this side want to go there, this side, but does not look this will be possible, and vehicles coming from this side wish to go there, but does not look possible. So, any of the movement of these vehicles are not possible, because there is a condition or there is a situation of the bottleneck here. So, this actually is the deadlock, and the similar conditions happens in the computer system as well. And the computer system also, there can be the processes which are requesting for several resources, and they may land up in the deadlock like situation, where the progress of any of the processes will not be there. So, there are two things here that you should know. One is the deadlock and the other one is the starvation. So, deadlock is like we have entered into the situation for which there is no solution. The solution will only be to kill a process and then resume the execution of the process. So, that process will be started from, or you can say that process will be restarted. So, that is the deadlock. But there is a situation of the deadlock sometimes. For example, when we are dealing with the process management, and CPU scheduling algorithm allocates the high priority processes to the CPU first, followed by the low priority processes. So, if the high priority processes are given the chance than the low priority processes, then there will be a starvation for the low priority processes, because in the system the high priority processes will keep coming. So, there are certain mechanisms by which the starvation can be resolved by the aging method. We have also already suggested this, that with the time you should actually increase the priority of the process, so that it does not get starved. So, the starvation is the condition in which there is a surety that the process will be, so the resource will be allocated to the requesting process sometime, but in the deadlock the requested resource cannot be allocated at any time. So, deadlock is an indefinite starvation, but the starvation is the scheme wherein, or the starvation is a situation wherein the resource may be allocated at some point of time, maybe sooner or later. So, these are the necessary conditions for the deadlocks to happen. We have discussed these conditions in detail. Just have a quick recap of these conditions: the mutual exclusion, hold and wait, no preemption, and cyclic wait. So, if a process, if you are dealing with a situation wherein a resource cannot be shared among the processes, and the situation is like our process is using a resource, so that resource cannot be allocated to any other process. So, we will say that this is the mutual exclusion. There is a situation also wherein a process is holding some resources and requesting for the other resources. Let us say a process is holding R1 and R3 resource, and the process is requesting for the resource R4 and R7. So, this is a situation wherein a process is holding some of the requested and requesting the new resources. No preemption means, let us say the same situation wherein the process is holding the request as R1 and R3, but requested resources R4 and R7 cannot be allocated at the moment. So, these resources R1 and R3 which a process requires for the execution, but process also requires additional resources R4 and R7 for the execution, and the execution of the process is dependent on all these 4 resources. So, those 2 resources R4 and R7 are not made available at the moment, R1 and R3 are allocated. So, P process is not using that resource, it is just acquiring that. So, better approach would have been that this P should free R1 and R3 also, but this is not allowed here. So, the system wherein the preemption or the forceful revocation of the resources from the process is not allowed. So, this is the third condition for the deadlock, no preemption. Another condition, cyclic wait. The cyclic wait represents that, let us say there is a process P1 and which is requesting for a resource P2, and there is a process P2 which is requesting for a resource which is currently being held by the P3 process. Let us understand it once again. P1 is a process which is requesting for a resource held by P2 process, P2 is requesting for a resource held by P3 process, and P3 is requesting for a resource held by P1 process. So, P1, P2 and P3, all 3 processes are actually in the cyclic wait. They are in the cyclic wait. The resources of any of these process or resource request of any of the process cannot be satisfied. They are in the dependency. So, this condition is the cyclic wait. So, if all these 4 conditions happen at the same time, we will say that the deadlock is there in the system. So, deadlock can be, or the process and the resources allocation can be represented with the help of the resource allocation graph in the system, and we have a process Pi represented by a circle, we have a resource Rj represented with a rectangle, and the dots in the rectangle represents that there are 4 resource units of this resource. For example, if we have 2 resource units, so a rectangle and 2 dots in inside the rectangle is representing the 2 units of this resource. If a process is requesting for a resource, then a request edge comes from Pi process to Rj. If the resource is allocated to the process, there will be an edge from resource to the process. So, this is the request edge and this is the allocation edge. In the allocation, the arrow will go from resource to the process, and in the request the edge will go from process to the resource. Now, this is these 2 diagrams which is showing the representation of the process and the request. Process P1 is requesting for R1 resource here, R1 is allocated to P2, R3 is allocated to P2, R3 is also allocated to P1. So, P2 is requesting for R2 resource, R2 is allocated to P3, P3 is requesting for R3 resource, and R3 is allocated to P2. If you clearly see that the P2 and the P3 process are in the cyclic wait, P2 is requesting for a resource held by P3 and P3 is requesting for a resource held by P2 process. So, they are in the cyclic wait, there is a deadlock in this resource allocation graph. The second diagram shows that, diagram on the right hand side shows that there is a cycle because of P1 is requesting the R1 resource, R1 is allocated to P3 process, P3 is requesting for R2 resource and R2 is allocated to P1 process. So, you can say that the P1 and the P3 processes are in the cyclic wait, but if you clearly see that there is a cycle, but even then there is no deadlock. Why so? This R1 resource is allocated to P2 process, P2 has no other dependency, sometime or the later P2 will complete. When P2 completes, this resource unit of R1 gets free. So, this resource unit request R1 was of P1, so that can be allocated to P1. So, cycle has been broken. Okay. Similarly, the R1 resource is allocated to P1, R2 is also allocated to P2. So, P1, so P1 will complete. Since P1 completes, it will free the resources R1 and R2. So, R2 resource, which is a request of the P3 process, can be allocated to P3 process. P3 already has been allocated at the R1 resource. Both the request of P3 has been satisfied. So, P3 can also lead to the completion. So, here we have a cycle, but we do not have the deadlock. So, the cycle does not actually mean that there is a deadlock. We have also said that if this is a single unit request model, cycle means a deadlock. If multiple unit resource models is there, cycle does not actually mean the deadlock. The deadlock may be there, or deadlock may not be there. After which we have seen the methods for handling the deadlocks. In the methods of the handling, we have seen the deadlock avoidance and the prevention scheme, which was taking the preventive measures for the deadlock not to happen in the system. Another scheme was the deadlock detection and the recovery scheme, which we will see in detail in today's class. This is about let the resources allocated to the process freely. Do not apply a check while applying when giving the resources to the process. If the resources are available, just give it to the process, and when the deadlock will happen in the system, we will take the corrective measures so that the deadlock can be resolved. Finally, the deadlock ignorance, which is the most popular technique for the latest operating systems. It is just like that the deadlock will be there because of a very few number of the processes. Ignore that, because there are thousands of the processes or hundreds of the processes running in the system. So, only one the deadlock happening out of or for one or two processes should be ignored. Now, the deadlock prevention scheme was suggesting that we have the 4 conditions. Let us avoid or let us deny any of those 4 conditions such that deadlock does not take place. So, we have 4 conditions: mutual exclusion, no preemption, hold and wait, and cyclic wait. So, if you do not let the no preemption take place, means by preempting the resources, deadlock will not be there. If you are denying the hold and wait, deadlock will not be there. If you are allowing circular wait not to take place, then deadlock will not be there. So, you have to deny any of the 4 conditions. It is sure that the mutual exclusion cannot be denied or mutual exclusion cannot be prevented, because the nature of the resource cannot be changed. If the resource is the dedicated resource, we cannot make it shareable resource. So, the another we have also seen that when we are dealing with the deadlock avoidance scheme, this was the second scheme, we are actually declaring the maximum need of a process at the beginning, or we are declaring that a process will require these resources and these many units in the for the execution. So, maximum unit requests have been declared at the beginning, and some of the requests can be given at this point of time, some later. Any of the requests given by the process should be seen in such a way that whether allocating of these resources leads to the safe condition or safe state of the system or not. If it is leading to the safe state, the resource request can be granted. If not, the process will wait. So, इसको हम कहते हैं फूक के कदम रखना कि if the request has been if the requested resources cannot be allocated to the process because it will lead to the unsafe state, that process will wait. So, here is a diagram that shows the safe and the unsafe state. Safe state means all the process can run to the completion if with the current need the resources are allocated to the processes. Unsafe means one odd process cannot be, or the request of one odd process cannot be satisfied. So, that is the unsafe state, and a very small subset of the unsafe state is deadlock. It means all unsafe states does not lead to the deadlock. There may be very few number of the instances, those will be the conditions of the deadlock. So, safe state, a subset of that is the unsafe state, a subset of that is the deadlock state. So, if a system is in the safe state, certainly there is no deadlock. If the system is in unsafe state, there is a possibility of the deadlock. We cannot say it clearly, but yes, there is a possibility of the deadlock. Avoidance scheme ensures that the system does not enter in the unsafe state ever. Fine. So, we have seen that these are the data structures that is required for the deadlock avoidance. The same data structures will be required for the deadlock detection as well. So, we will deal with this in detail, and then we will quickly take the example to understand the deadlock detection and the recovery scheme. So, these are the data structures. Let us say there are n number of the resources and m number of the resources, n number of process and m number of the resources. So, available says that how many units of one resource is available, how many unit of the second resource is available, and how many units of third resource is available. So, this is represented with the help of a vector. Let us say it is representing 7, 3, 4 and 9. So, this means that the for resource R1 7 units are available, for resource R2 3 units are available, for resource R4 R3 4 units are available, and for resource R4 9 units are available. So, this is the available vector. Maximum means how much is the maximum demand of a process, how much is the maximum demand of a process. So, this is declared at the beginning. So, maximum is a obviously 2D matrix. So, maximum will be M cross N matrix, where N cross M matrix, where N is representing the number of processes and M is representing the number of resources. Okay. If you say that there is some I row n j column in the matrix, so the entry max I j will be representing that what is the maximum requirement of process I for resource j. What is the maximum requirement of process I for resource j? Similarly, we have the allocation. This tells you that how much maximum how much resources have been allocated to a process. So, if the allocation matrix says that this is I row and j column, so the entry allocation I j will be telling you that how many units of j resource is allocated to the process I, how many units of j resource has been allocated to the process I. Similar is the need. We already know that the maximum is there, how much maximum will be demanded by a process. We also know that the allocation is there. So, maximum minus allocation will be the current need. Okay, current need means how many additional resources will be required for the process in the future, citing that some of the resources have already been allocated. So, need matrix will also be declared like this. So, knowing maximum and the allocation, we can find out the need by this formula. Need I j will be equals to maximum I j minus allocation I j. Obviously, maximum minus allocation will be the need. Now, this is a question which says that a system has 4 processes and 5 allocatable resources. The current allocation and the maximum needs are given as follows. The available number of resources are 0 0 x 1 1. Here we have to find out what is the value of x such that the process state is safe. Okay. So, we have to calculate the value of this available such that we have the state of the system as safe. So, for this what we will have to do, you will first have to, I am just telling you the ways, you can do it by yourself. You just need to compute the need. Need can be found by maximum minus allocation. For example, the need for the process A will be 0, 1, 0, 0 and 2. Okay. So, by the available resources you can see that the need of the first process currently cannot be satisfied. Similarly, if you take the need of the second process, so this will be 0, 2, 1, 0 and 0. So, you can clearly see that the need of this process also cannot be satisfied at the moment. So, the need of the third process will be equals to 1, 0, 2, 0 and 0. Now, you can see that the need of this process can also not be satisfied. There is no match with the available. So, up to now neither A can complete, nor B can complete, nor C can complete. Let us see for the D. So, for the D process it will be 0, 0, 1, 1 and 1. Yes, there seems to be the possibility 0, 0, 1, 1, 1. So, if we have x as 1, let us say we take x as 1. So, the need of the process D can be completed. So, process D, it means PD can complete. If PD completes, it frees all its resources. So, the allocated resources to the process D are 1, 1, 1, 0. So, these are added to the available ones. So, this becomes 1, 1, 2, 2, 1. You can see with which it will match. So, with whichever need can be matched with this, that need can be satisfied. For example, it can be matched with PC also and PB also. PA cannot be satisfied at the moment. So, similarly, this scheme will update the values and you can find out the value of x, such that if this scheme is not good, means x equals to 1, then take x equals to 2 and find it out, and then take x equals to 3 if 2 is also not enough. So, the deadlock detection algorithm is also very similar to this. What we will do, that the deadlock detection allocation scheme will freely allocate the resources, and when the resources are given to the process, this may lead to the deadlock. You periodically call the deadlock detection algorithm, and that will be telling you if there is a deadlock, then take the necessary action. So, there are two mechanisms by which this can be done. One is for the single unit resource model and one is for the multiple unit resource model. So, for the single unit resource model, this is the resource allocation graph on the left hand side. On the right hand side, we will build the wait for graph. So, what is the wait for graph? This is the dependency diagram between the processes. So, here you can see that the P1 process is requesting for R1 resource and R1 is allocated to P2. I am just putting a tick mark so that you can understand. So, P1 is requesting for resource R1, which is allocated to P2. So, P1 and P2 are in the dependency condition. So, similarly, P2 is requesting for a resource which is held by P4 process. So, P2 and P4, they are in the dependency. Then P4 is allocated to P4 is requesting for R2 resource, which is held by P1 process. So, P4 and P1, they are in the dependency. Similarly, you can see that P2 process is requesting for a resource R4, which is held by P3. So, P2 to P3, there is a dependency. Fine. Now, P3 process is requesting for a resource R5, which is allocated to P4. So, P3 and P4, there is again a dependency. Okay. Now, P2 process is requesting for R3, which is allocated to P5. So, P2 to P5, this is also a dependency. So, this is the wait for graph for the given resource allocation graph. So, in case there is a cycle, there will be a deadlock. Now, you can see that there are two cycles. One cycle is P1, P2, P3 and P4. Another cycle is P1, P2, P4 and P3. Sorry, P1 and here P1. So, this includes 4 processes and this includes 3 processes. So, we actually have detected the deadlock. Now comes the recovery scheme. So, the recovery scheme suggests that you should actually stop one of the processes. So, you kill one of the process and let us see that if the deadlock is resolved. So, if by deleting one of the process deadlock can be resolved, that is considered as the good scheme. For example, let us say we are going to delete the process P2. So, if P2 is deleted, P1 completes. If P1 completes, it releases resources P4 completes. If P4 completes, P3 will also complete. So, the deadlock can be resolved like this. Now, the another one is the use of the same data structures. As I told you, we already have explained this in detail. So, the deadlock detection algorithm says that multiple unit request model is there. You should first declare that all the processes cannot finish. Okay. So, the finish for all the processes have been false. Okay. Initially, the finish of all the processes are false, and then we are executing the deadlock detection algorithm. So, deadlock detection algorithm says that if no resource are allocated to the process, obviously that process has finished. Okay. If no resources are allocated to the process, that process has finished. That is what we will assume. So, if even a single request is or single unit of any resource is allocated, we will consider that process is not finished. So, if allocation is not 0, finish is equals to false, otherwise finish will be true. Okay. So, if finish is false, we are interested. If finish is true, we are not interested. So, if finish is false and request is less than or equal to the available number of resources, इसकी request को हम satisfy कर सकते हैं जो इसने request किया है. So, what we will do that इसकी request को हम satisfy कर देंगे और request को satisfy करने के बाद process हमारा finish हो जाएगा. So, if process finishes, all its allocated resources will become free and will be added in the work. So, finish I is equals to true. So, we will see it for all the processes one by one. We will see for all the process. So, अगर एक भी process मुझे ऐसा मिलेगा जिसको कि हम complete करा सकते हैं, तो हम देख लेते हैं, finish करा सकते हैं. If the finish of all the processes are true, then we will say that the system is not in the deadlock. But लेकिन एक भी resource, एक भी process अगर फिनिश false है उसका तो we'll say that the system is in the deadlock. Okay, so this mostly works on the principle of the safety algorithm, just a slight variation from the safety algorithms. For example, अगर हम ये देखें इस क्वेश्चन को, तो in this question the request of the process are given. This is the request and this is the available number of resource A, B, C 0, 0, 0, no resource is available. Can we actually lead to the completion? You can see that all these process P0, P1, P2, P3, P4, they have been allocated some resources, so their finishes are false, they are not finished well as of now. Now after this you can see that with the 0, 0, 0 resources you can fulfill the request of process number P0. So P0 completes. When P0 completes, its allocated resources will be added in the available one. So 0, 1, 0. Now after this you can see that with 0, 1, 0 you can satisfy the request of P2 also. So let's satisfy the request of P2. P1 P0 को हमने true कर दिया है, P2 को भी हम free कर देंगे क्योंकि P2 complete हो जाएगा. So 303 resources will be added. So 3, 1 and 3 resources are available. You can see that with this 313 you can satisfy this request and this also. So it means that you can satisfy all the requests. So system is not in the deadlock. But if you look at this one or this scheme wherein we have just changed, where we have a slight variation in the question than this one, where P2 की request को हमने 000 की जगह 001 कर दिया है. Okay, so 001 cannot be satisfied, और अगर 001 satisfy नहीं होगा तो आगे किसी का progress नहीं होगा, सभी false रह जाएंगे. तो P0 completes, yes, P0 की request 000 है, satisfy की जा सकती है, but we cannot satisfy the request of any other process. You can see it with the pen and the paper. So we will say that the process P1, P2, P3 and P4 are in the deadlock. Fine. Now you can take this example also to solve by yourself. This is representing that the resources are there, the resources are allocated to the processes. This is the resource allocation graph by which you can find out what is the current allocation. I will do it for one process, rest of the same things you can do by yourself. So for the P0 process, 1 unit of R1 is allocated. For the P0 process, 1 unit of R2 is also allocated. For the P0 process, no unit of R3 is allocated. And what is the request? P0 process is requesting for 1 unit of R1 and none else, so it will be 0 and 0. Similarly, you can find out the allocation of the other process. Now what about the available? You just look at the dots inside the rectangles. So this is 2, all those 2 are allocated. So 0 units of R1 is available. Then for R2, 3 units are allocated, no unit of R2 is free, but R3, 1 unit is free, this one. So this is the available. So after making this matrix, by applying the deadlock detection algorithm, you can find out if the state of the system is safe or not. I have built it for you, but you should do it by yourself and compute the results by setting the finish of all the process as true and finish of all the process as false, and then find out which of the process can complete. Okay. Now for this example, you can see that the available is this, so you can satisfy the request of P2. So first P2 can finish. When P2 will finish, all its allocated resources will be free. So the total available then will be 0, 1 and 1. With 0, 1, 1 you can satisfy the request of P0. So then P0 frees. So 1, 1, 2 is the new available. You can satisfy the request of P1 then. So P1 frees and so 2, 2, 2 is available after the P2 completes. Sorry, after P1 completes, and finally you can satisfy the request of P3 also with this. So all these can complete. So you can say that the system is not in the deadlock. Now there are recovery schemes. A recovery scheme suggests that which process should be aborted. You should actually select the minimum number of processes such that minimum number of processes can be deleted or killed and the system recovers from the deadlock. So there are certain schemes that you can see which of the process should be selected as a victim. So, this can be based on priority, this can be based on how long a process has executed and how long is remaining, and many more schemes that can be suggested. Another scheme may be to roll back the resources, not kill a process, but roll back some of the resources. So, you will first have to select the victim. So, after the selection of the victim, whichever minimizes the cost, you will select that scheme. Okay. So, if you are selecting one process only every time, so there will be starvation, there may be the starvation for some of the process. So, killing a process and rolling back the resources is the scheme for recovery from the deadlock. So, that is all for today's lecture. These are the references for today's lecture. Some of the diagrams in the first slide have been taken from the mentioned site. The rest of the concepts has been taken from operating system concept by Shilber, Shadjan, Galvin. Thank you.